Hi everyone, I'm Abhijit and this is Greg and Akan. And our senior design project is design a water flow measurement system sponsored by IHR. So our system is supposed to calculate speed of water, relative depth, and wave velocity in real time, acquire those readings, and provide the user with a graphical and tabular format to see those readings. It's also supposed to save data for future use. The system should be, or the devices should be able to power from multiple sources, and one of the major design constraints was to have a water-resistant enclosure. And there's 3 different devices that communicate with 3 different instruments to get water flow data. And to do that, we need a multiple device communication protocol. So here's our simple system overview. As you can see, there's 3 different instruments: a pygmy meter, which is essentially a pinwheel that rotates as water is flowing into the pins. And every revolution that it makes, it has a switch closure, which we detect and track to get water velocity. The other 2 instruments are cap wire instruments, which have a metal plate and a string, and which are partially submerged underwater. As you rise it or lower it in water, the capacitance changes in those instruments, and we track that using our 2 circuits and related that data over to our PC.
So here's an overview of our circuit for our pygmy meter instrument. So you can see over here is the microcontroller, our PIC microcontroller, which takes in readings from the pygmy meter itself. Since it closes a switch, we have it closed the switch between our input pin and ground, so it is a normally high pin using pull-up resistor. And so the microcontroller basically sees a square wave, and so it collects the data from that, finds what frequency is at this moment, does a calculation, and sends the data out through the RS-45 serial chip here to our PC. And we also have a selectable power supply up here. We can select between a 9-volt battery and an external 12-volt source, which we got from a wall outlet, which was, of course, regulated down to 12 volts DC. And so then we have a regulator, which takes everything down to 5 volts, which is what our circuit operates at. And we have a very similar circuit for the cap wire instruments, but instead of a pull-up resistor, we have a 555 timer, actually, which incorporates the cap wire instrument as a capacitor in its circuit. So then the output, square wave output from the 555 timer varies in frequency depending on what the capacitance of the cap wire is. So the frequency will be proportional to the depth. So the microcontroller reads that data and sends it to the PC. Okay. So in order to make our circuits compact, robust, and aesthetically pleasing, we have a PCB manufactured at the eShop. And this was designed with Eagle software. And we also needed a water-resistant enclosure, which was designed in Pro-E and manufactured at the EDPC, made with a rapid prototyping machine. So here's a few of the challenges we faced in getting our design to work. The first of which was learning a new programming language, PIC Basic. And in order to do that, we had a new IDE for us, which took some time to set up, but didn't take terribly long to learn the new language. So let's see, we've got the RS-45.
Yeah. The next challenge that we had was RS-45. Since we have 3 different devices on the same bus, we we can use RS-232 because RS-232 is a one-to-one protocol. So we use the RS-45 protocol. RS-45 is just a hardware protocol which says that you have a bus between your instruments, the devices, and the bus has 3 lines, one ground and 2 lines A and B, which are the inverse of each other. If A is 1, B is 0, and if B is 1, A is 0. And since most PCs they don't have any RS-45 hardware components, we had to use a RS-45 to RS-232 converter, and then that changed the levels of voltage to which the PC can understand. And also for the RS-45 standard, since it's a hardware protocol, we had to take into account the issues of bus jamming. Basically, if multiple devices send data on the bus at the same time, all the data will be invalid and packets will be lost. So we had to make our own protocol for sending data across the bus. Basically, the PC sends some value on the bus. All the components they see the value. It's basically an address value, and each component sees that it's its address and send data accordingly. Over to the enclosures.
So another major challenge that we faced in this project was actually designing the enclosures. As EE engineers, we have no, or as electrical engineers, we have no exposures previously before this project to actually use Pro-V and work with multiple dimensions and design something. So we use a help of a mechanical engineer, Andrew Beadle, and made our initial prototypes, and then went to the machine shop and made it perfectly compatible with our PCB so that water can't leak into the actual circuit.
And is the design.
Yeah.
And perhaps the biggest challenge was moving our design from an ideal lab environment to the environment is actually going to be used and interfacing with our instruments. For example, we had previously used a function generator to generate a square wave to test out our pygmy meter circuit. But of course, the pygmy meter doesn't output a perfect square wave. So there was there's a good deal of bouncing phenomenon in the circuit, which had to be taken care of in our microcontroller firmware. We had to do some debouncing there. And one thing that we ran into that we didn't expect at first was how important good connections are to having something that works. If even one connection is a little bit off, then there's all kinds of flaking behavior which seems to be unexplained.
Yeah, and so in the end, we were able to meet all the specifications that we had to achieve. The one important specification is that the interface had to be as friendly and easy to use as possible. So for that, we have a single application in which the person can choose the values of the COM port, baud rate values, and also they can and also with that we were able to show a chart which changed as the values actually changed in real time. For the water velocity, we were able to achieve our accuracy of 0.1 feet per second up to 4.8 feet per second. For the water depth, actually, our goal was 0.1 feet value of accuracy, but we were able to exceed that, and we got a 0.05 feet accuracy. And also we were able to use the wave depth data from both the CAP bars at a known value and length of each other, and we were able to get the wave speed as well from 0 to 1 feet per second, because our entire system just works on slow moving waves. And also for ease of use for the end user, we have all the values shown in a text box, in a chart, in a table, and also in a text file. As you can see, that's a sample output of our data, which gives you all the data which you got from time.
So after we were meeting all these specifications, we were trying to look back on how this project went overall during the semester. And we realized how important it is for any design project to be planned properly from the start. We scheduled our meetings at least 3 or 4 times per week. And we thought at first that it's a simpler project as compared to some of the other electrical engineering projects. We'd be able to finish it off in a month or so, but there's multiple factors that can go wrong in a project which need to be taken into account. So our planning, our team schedules, and our planning for this project helped us to basically give us enough time to work on those problems and manage certain risks in terms of circuits not working, connections problems, communication problems, and things like that. And most importantly, as Greg mentioned before, going from a lab setting to a real setting. So we were able to take that into account and demonstrate the project successfully to both our sponsors and professor.
Special thanks to our sponsor, Gregory Wagner, and to Professor Cliff Curry. Couldn't have done it without you guys.
At this point, I'd like to open it up to questions.